So in this lecture we discuss about the hydraulic machineries. So hydraulic machineries here we consider as a turbines and pumps as a hydraulic machinery. So turbines extract energy from the fluid and convert into the mechanical energy. Mechanical energy in the form of the rotation or rotary motion along with some torque. So this particular mechanical energy in form of the rotary motion and along with the torque. Another machinery, hydraulic machinery, we can consider as a pumps. So these are utilizing energy, mechanical energy, and convert it into the hydraulic energy or add some energy to the fluid. So these two type of the hydraulic machinery we consider as a turbines and the pumps. So we discuss about the turbines. So these turbines here we discuss about the hydro turbines. So that turbines work by utilizing energy available in the water, and that energy is converted into the mechanical energy. So these hydro turbines are generally utilized for the power generations. So these are generally utilized for the power generations. So these turbines convert this hydraulic energy into the mechanical energy, and this mechanical energy is attached to the generators, and that generators are then converted this particular mechanical energy into the electricity or electric energy, and this particular hydroelectric power is the cheapest source of the power generation. So normally this particular type of the turbines are utilized for the power generations. So these turbines is first introduced by Ponslet. So Ponslet introduced first as a water wheel. So energy from that particular water is utilized for rotating that particular water wheel. Again it redeveloped or modified by some inventors, and according to that inventors or by that inventions by that inventors, that name given to the turbines according to the name of the inventors as a Pelton turbine or Francis turbine or Kaplan turbines. So these are the name of the inventors who invent or modified that particular old water wheel, and they modified, and that name is given by of the inventors. So that name is according to that inventors' names. So if you consider this hydro turbines, these are that water stored backside of that particular dam, that is supplied to that particular runner through large pipes. So generally it is called as the penstocks, and that water energy is utilized in the turbines, and it converted into the some useful energy, mechanical energy, and that again converted into the electricity or electric energy. So there are number of classification criteria for the turbines. So here few classification criteria are considered. So here as a head and quantity of the water available. Second is the hydraulic action of that particular water that utilized in that particular turbine. Direction of the flow of the water in that particular with respect to the runner. Specific speed of the turbines, and disposition of that particular shaft of that particular runner. So first criteria is that classification of the turbine as per the head and quantity of the water. So as per the head available, we can classify that turbines as a high head turbines, medium head turbines, and low head turbines. So these high head turbines are generally considered when that head available, when a head available more than 250 meters. So we can consider that high head turbines above 250 meters. So in this type of the turbines, that water quantity utilized for the conversion purpose is a small one compared to the medium head and the low head type of the turbines. So this type of the turbine is invented by this inventor Pelton. So that name is given to the turbine as a Pelton turbine, and these are suitable for the high heats. So for high heat turbines or Pelton type of the turbines, is small quantity of the water is required compared to that medium head and the low head. Second type is the medium head type of the turbine. For this type of the turbines, that head range in between the 40 meter to the 250 meters. So it required a medium quantity of flow of water. So it is invented by the Francis by scientist as a name given as a name as a Francis. So that inventor name is given to this turbine. So it is called as a Francis turbine or medium head type of the turbine. Third type is the low head type of the turbine. So these turbines are work under a head less than 45 meters. So these are called as the low head turbines, and it is invented by the Kaplan. So that name to this turbines is given as a Kaplan turbines, and these are suitable for the low head type of the turbines. Again, these type of the turbines, these turbines utilizes water energy, may be in form of the kinetic energy or pressure energy. So according to that energy utilization or that hydraulic action of that particular water utilizes in that particular turbine, they are again classified as a impulse type of the turbine and the reaction type of the turbine. So first type is the impulse type of the turbines. So in this type of the impulse turbines, here that impulse action of the water we can observe, and if you consider that impulse type of the turbine, these are suitable for the large heads. So for large heads, Pelton wheel or Pelton turbine come into the picture, and in Pelton turbine that runner is rotated by utilizing that water jet, and that water jet strike to that particular runner in tangential direction. So these are also called as a tangential flow type of the turbine. Again in next slide we discuss about that particular. So this particular action of the water available in this particular turbine is a impulse type of the action. So that particular water strike to that runner or impulse to that, having impact or impulse to that particular runner, so it is called as the impulse type of the turbine. Another type is the reaction type of the turbines. So Francis turbine and the Kaplan turbines, so medium head and the low head turbines are called as the reaction type of the turbines because they utilizing pressure energy. They utilizing pressure energy available in that water. So these are called as the reaction type of the turbines. So third type for classification of the turbine is the according to the direction of the flow of water in that turbine. So as these directions are given as a tangential, radial flow, axial flow type turbine or mixed flow turbines, these directions are considered with respect to the runner. So how that water enters to that particular runner and how that water leaves that particular runner. So that water direction at the entry and at the exit of that particular runner is considered for this classification of the turbines. So these are classified according to the direction of the flow of water with respect to runner as tangential flow turbine, radial flow turbine, axial flow turbine and the mixed flow turbines. So these directions with respect to the runner, So first we can consider as a tangential flow turbines. So this particular tangential flow we observe in the high head turbines or impulse type of the turbines, and these impulse type turbines are generally we consider as a Pelton turbine. So in that Pelton turbine, that water hit that particular runner or strike to that particular runner in tangential direction. So to that particular runner, water entry and exit is a tangential. Water entry to that particular runner is a tangential. So it is called as a tangential flow turbines. Second type of the turbines according to direction as a radial flow turbines. So in this particular radial flow turbines, water enter to that particular runner in radial direction. So pure radial flow turbines entry and exit in the radial direction. So pure radial flow turbines are not in use in these days. So instead of this pure radial flow turbines, mixed flow turbines are utilized. In the axial flow turbines, again in third type, axial flow turbines, that water enter to that runner axially and leave that particular runner axially. So in Kaplan turbine, so these particular runners in that particular Kaplan turbine is placed under the spiral casing. So in spiral casing, water enters radially, but that radial direction again converted into the axial direction while entering to the entry or inlet to that particular runner. So that's why it is called as the axial flow turbines. So we consider the direction of the flow of water with respect to runner. So in Kaplan turbine, water enter in that particular casing radially, and through that radial entry again converted or transferred to in axial direction, and entry point at the particular runner is in axial direction. So these are called as the axial flow turbines. So normal turbines we can observe as the Kaplan turbine as the axial flow type of the turbine. And last point is the mixed flow type of the turbines. So in Francis turbines, that water enter through casing, water enter to that particular casing to that runner in a radial direction, and again it leave to that runner in the axial direction. So mixed type of the directions we observe. Entry at the runner radially and exit from that runner is in axial direction. So this mixed direction to that with respect to that runner we can call as a mixed flow type of the turbines. So these are normally observed in the Francis type of the turbines. So we can call as it is a mixed flow type of the turbine. So as per next criteria is the classification based on the specific speed of the turbine. So specific speed of the turbine we can consider as a speed of the geometrical similar turbine which produce unit power when working under the unit heat. So this particular specific speed is utilized for the classification. So for Pelton wheel, that specific speed is under range 8 to 30. For Francis turbine, that specific speed in between 52 to 250, and for Kaplan turbine it is in between 250 to 850. So according to the classification, according to the specific speed of the turbines, these are classified as a for Pelton turbine from 8 to 30, for Francis turbine it is in between 50 to 250, and for Kaplan turbine it is in between 250 to 850. Again, based on the disposition of the shaft of the runner, that classification in this generally it is a arrangement. It is arrangement either it is vertical or horizontal. So according to that arrangement of that particular setup, we can classify it as a disposition of the shaft of the runner. So Pelton turbines are having setup with a horizontal shaft, whereas other types are having vertical shafts, maybe horizontal or maybe vertical. So according to the arrangement of that particular turbine, it is classified as a horizontal type or the vertical type. So next point we can consider as a heads, losses and the efficiency of that particular turbines. So head we can consider as a head we can consider as the water level available or that height of the water in that particular reservoir we can consider as a head. Now gross head, we can consider that gross head. So that particular head we can measure in between headrest level and the tailrest level. So tailrest is the from the exit of the turbine. From the exit of the turbine, that water is again transferred to the river. So that particular head difference in between a headrest level and the tailrest level, that you can consider as a gross head. In this particular gross head, if you consider that friction losses, now with consideration of the friction losses, that gross head now reduced with head loss in the friction. So that available head by considering that friction losses is called as a net head. Now if you consider losses, that losses we observe in the penstock and the elements in that particular turbines. So we can consider that losses, that head loss in the penstock, or head loss in the nozzles, and head loss in the turbines, maybe in the form of the ED currents, maybe in the form of the ED losses or formation of the EDs, or friction losses that observe in the blades, or some losses we observe in the draft tube, or energy available or losses through that particular living water, that we consider as a hydraulic losses. So these losses we observe at the entry of that particular water to that runner through penstock, again the nozzle, again losses in that particular units available in that particular turbines, maybe draft tube, or maybe blade friction, or maybe eddy formation, or kinetic energy living through that particular water. So again here consider as a leakage losses. So some losses through that leakage we can observe. Again mechanical losses are generally considered with the friction losses, generally it is related to the friction losses. Again in the generator losses, that losses in that particular generator, it is called as the generator losses. So when you consider losses at the different stages, and if you consider that losses, and if you compare that transformation of the input energy to the output energy, and with this particular hydraulic losses, then it is called as a efficiency. So transformation of the input energy to the output energy, and how much losses are there while transforming this input energy to the output energy at different stages. So at different stages, that input energy transformation to the output energy, and conversion of the loss, and the consideration of the losses, these efficiencies are come into the picture. And if we consider that efficiency at the different stages, for the different stages, their names are given as a hydraulic energy, mechanical energy, etc. So hydraulic efficiency or mechanical efficiency, etc. So these efficiency are consider losses at the different stages. So first efficiency we consider as a hydraulic efficiency. So it is a ratio of, so these are the, again it is output divided by input, but these are considered at the different stages. So first here that hydraulic efficiency, ratio of the power developed by that runner to that actual power supplied to that runner. So how much power developed by that runner and how much power supplied to that runner, that ratio we can consider as hydraulic efficiency. So runner output we can consider as the runner output divided by the actual power supplied to that runner. Next efficiency we can consider as a volumetric efficiency. So these are by considering volume available to that particular runner. So that ratio of the actual quantity of water striking to that runner blades to that quantity of the supply to that particular turbines. So that volume of the water is considered in that particular volumetric efficiency. Third type of the efficiency here, that ratio of shaft output to the runner output. Ratio of shaft output to the runner output we can consider as mechanical efficiency. So here we consider that mechanical losses. And last one is we can consider as a overall efficiency. This overall efficiency, it is a considered as a shaft output to the net power available. Shaft output to the net power available. So generally it is a output or power. We can consider as a output power divided by the input power. That input power is given by the power available or power given through that water flow, and the output power we can consider the shaft output power. So these type of the efficiencies we can consider. So these efficiencies are considered that particular losses, and if you consider these losses at the different stages, we can give this different names as a overall efficiency, and the hydraulic efficiency, different names are given for that particular stages.